Record this. We're playing around with three things right now. Sequences. And remember, sequence is just a list of numbers. Like we rely on the counting sequence, 1, 2, 3, 4, and that just goes on forever. Another sequence that's very popular might be 1, 1/2, 1/4, 1/8. So in this one right here, I am doubling the denominator or multiplying by 1/2. You can take either approach. I'm going to say I'm multiplying by 1/2 each time. And so this would be 1/2 to the n minus 1 if I start counting for n at 1, 2, 3, 4, and so on down the road. In this list, again, when we talk about sequences in calculus, it's usually an infinite sequence. And the question then is, what is the limit of this? Where is it heading to? Right? When we count, that goes to infinity. It's a divergent sequence. We count forever. It keeps getting bigger and bigger and bigger. But here, numbers are getting cut in half and half and half, but they're always positive. So the smallest we can possibly be there would be 0. So we would have some evidence that the limit is 0. Sequences are often written with subscripted notation. Like in this case, an would be equal to 1/2 to the power n minus 1. And here I believe that the limit, as n goes to infinity, of that 1/2 to the power n minus 1 is equal to 0. So sequences, they're just lists of numbers. They're just limits, like limits of functions we played with in Calculus 1. What are our tools for working with sequences? Well, our tools are in part our intuition about what a list of numbers is doing. But we also have some rules like related to polynomials. Like take the sequence a sub n is equal to, how about n squared plus 1 over 3n squared minus 7. What can we say about this sequence? Well, anytime you see a sequence, I would say either on paper or on a calculator, you should list some terms in that sequence. What do they look like? So usually we count with sequences at 1. So if I plug in 1, the first term here would be 1 plus 1 over 3 minus 7, which would be 1 over -4. And the next term would be n equals 2. That would be 4 plus 1 over 12 minus 7. So the next one would be 5 over 5, interesting, which is 1. The next one with n equals 3 would be 9 plus 1 over 9 times 3 is 27 minus 7. So that would be 10 over 20, which we could reduce to 1/2. And then we can keep getting more of these to try and get an idea about what it's doing. Now, it's getting to the point where a calculator would be a better thing to look at. Typing sequences into a calculator usually isn't that easy, but instead we could do something like enter it as a function of x. So I could just go to Desmos here, enter that as a function of x instead of n. X squared plus 1 over 3x squared minus 7. Now, I only care about the points, the whole number of points on this function, not the whole thing. So really, as far as this function is concerned, I only care about, again, when n is equal to 1, 2, 3, 4, 5, 6. But looking at the graph, I'm kind of getting a sense for what's going on here. It looks like it might be convergent. Some of you may have looked at this and said, oh, well, I recognize this from working with functions way back in math 251, calc 1, limit as n goes to infinity of a polynomial where the top and bottom have the same degree is going to be the ratio of the leading terms, which would be 1n squared over 3n squared, or 1/3. So we believe that this thing should be heading toward 1/3. If we look at the graph, we should be able to graph y equals 1/3 and see, oh yeah, look at, they're converging together. So we can zoom in. Here they look like they're on top of each other, but they're not quite. but it looks like it's converging there. What does it mean for a sequence to converge? Convergence means the limit is a real number. What does it mean to diverge? The limit is not a real number. So sequence divergence just means the limit is not a real number. Simple examples of that, if we took an to be n squared, as n gets big, the square gets bigger. The limit of this sequence is infinity. Infinity is not a real number. So we would say this is divergent. But if we had a sequence Bn that was -1 to the n, what's that limit? Well, here we might want to list some terms. The first term here, if n equals 1, is -1. When n equals 2, it's -1 squared or 1. When n equals 3, -1 cubed is -1. This one is just going to alternate between -1 and 1 forever. Does this ever settle down to a real number? The answer is no. It bounces back between two real numbers forever and ever. There is no specific number for this limit. It is divergent. Why? Because it doesn't converge to a real number. Sequences in the analysis and calculus are limits. I'm pointing that out specifically in our review here to think about our work with series. What does series mean? It's another word for series. Starts with an S. Sum. Series is a sum, not a list, but a sum. Like what happens when we add a bunch of stuff up? Like in the previous examples, I could add up a bunch of n's as n goes from 1 to infinity. I could add up powers of 1/2. There, I might start at 0. I could add up some funky fraction. In this case, n goes from 1 to infinity. Series are a little more complicated than sequences, but we need to know about sequences to figure out what series do. Right? So for example, one of our most powerful tools, the simplest one, the first one we looked at, is called the divergence test. What does the divergence tell us? The divergence test tell us. It only tells us if a sequence diverges. It doesn't tell us if a sequence converges. Divergence test basically says if the limit of the terms, the sequence, those would be our BNs, we usually call them. If that limit, as n goes to infinity, does not equal 0, then the sum must diverge. What if the sequence does go to 0? Divergence test tells us nothing, absolutely nothing. Then we have to seek out another test. All of the tests that we learn do not apply to sequences. Sequences are just limits. So we can't do something like whip out a ratio test to talk about what a sequence is doing. That only applies to series sums. And we got to keep that in mind when we're exploring these things. So thinking about the divergence test for a minute, what's n doing as n goes to infinity? Well, it's going to infinity, not 0. So this thing must diverge according to the divergence test. Diverges. How about this one right here? What did we decide about the limit as n goes to infinity of 1/2 to the n? Well, that goes to 0. So the divergence test would be inconclusive. I need another test to figure this one out. I'm just going to put a question mark there for now. How about this one right here? What's the limit of these terms? its limit is 1/3. Is that 0? The answer is no. So the divergence test says this sum right here will not converge. It must diverge. And you could add them up to see. Sums are a little easier to do in a calculator like Desmos than sequences are. So just for fun, I'm going to test this out. Sum as n goes from 1, I can't go to infinity. I'll go to 10 for now. That fraction, n squared plus 1 over, what do I have, 3 n squared minus 7. And here I can see if n is 10, I get 3.56-ish. If n is 100, I get 33.65-ish. If n is 1,000, I get 333. If n is 10,000, I get 3,333. And it looks like with every power of 10, this thing is getting 100 times bigger than it was before. So it does seem to be diverging according to the first 10,000 partial sums. It's a lot of partial sums. How did we figure out a series like this for convergence or divergence? What type of series is this? It's a geometric. And we developed a rule for geometric series that says as long as this base here, which we call R, in absolute value is less than 1, that implies convergence. Otherwise, it diverges. My R here is what? 1/2. Let's pitch in the convergent version of these guys. And not only does the geometric series say it converges, but geometric series, we also prove what converge to. We converge that we prove if it does converge, it's always going to converge to A, the first term, divided by 1 minus R. And again, this series right here was 1 plus 1/2 plus 1/4 and so on. So this series in its limit, which means you have to add forever, which isn't quite possible, has to converge to 1 over, first term is 1, 1 minus 1/2, which would be 2. So we should see as we add up partial sums, those partial sums are getting closer and closer to 2 the farther we add out. And we made a list of a bunch of other tests that we could apply. We had the limit comparison test. We have the integral test. We have the ratio test. We have the root test. We have the direct comparison test. And every series of numbers we see, we had to evaluate which test should we use. And sometimes the test works and sometimes it doesn't work. And we have to try something else. We extended this idea one more time, right? We started with lists, then we looked at sums of numbers, but then we looked at infinitely long polynomials. Taylor series, or sorry, power series. Power series is an infinite polynomial. And we discovered that some of these infinite polynomials are actually useful, like the sum as n goes from 0 to infinity of x squared. That's just a geometric series. It's going to converge to 1 over 1 minus x if the absolute value of x is less than 1. It's just a geometric series where I put an x instead of an r. And then we tweaked that in many ways and found other functions. Like if I substitute in here a negative x for an x, then I get the function 1 over 1 plus x is the convergent function for the series that alternates. We integrated that series to get a new one. We differentiated that series to get another new one. We did other substitutions in there, and we ended up with series for the natural log, for the arctangent, for the hyperbolic arctangent, among other functions. So one version of power series is where we tweaked the geometric series. Also, we can just make up any series we want. We can just make up a set of coefficients. But we also found a way to generate them. That was Taylor series. And Taylor series generates series of existing functions based on derivatives. So the coefficients for Taylor series are the nth derivative, where we plug in some central value we call a, and divide by n factorial. And this was a new way to generate series. So a general Taylor series looks like sum as n goes from 0 to infinity, coefficient, nth derivative evaluated at a divided by n factorial times x minus a, whatever central x value we pick, to the power n. And with that, we found series for e to the x. We found series for the sine of x, the cosine of x, and we extended those to other functions. And we did one other way to find new series. That was the binomial theorem. Binomial theorem tells us if we start with something like, I'm just going to use the basic one, 1 plus x squared, but it could be more complicated than that. Or sorry, 1 plus x, excuse me, to the power r, then that's going to be equal to the series as n goes from 0 to infinity. Coefficients look like r times r minus 1, all the way down to r plus n minus 1. Sorry, r minus n plus 1. Minus n plus 1 divided by n times n minus 1, all the way down to 1 times x to the n. And that's always going to look like 1 plus r times x plus r times r minus 1 over 2 times 1 x squared, r times r minus 1 times r minus 2, 3 times 2 times 1, x cubed, and so on. So without taking repeated derivatives, that allowed us to find series for things like 1 plus x to the power 1/2 and 1 plus x to the power -3. Or even things like 1 plus x to the power 4.1 and so on. All right, so big ideas again for the last 2 chapters. We have sequences, which is lists of numbers. We use limit ideas to analyze them. Listing out some terms is helpful. We have sums, which is adding up a list of numbers. Writing out some terms is often helpful. We have a ton of different tests we use to evaluate these. And then we have power series, which are series with variables in them. In like we have n the counter, now we have x the variable in there. Important thing about power series is finding an interval of convergence. What is our most powerful tool for identifying an interval of convergence? The ratio test. The ratio test will find a radius of convergence for us, and then we have to test the endpoints to see if they're in or not for convergence. The ratio test didn't work. What else would I apply? Sorry, root test. The root test is the next one. Yeah, ratio tends to be most useful. Root test in other places where the ratio test doesn't seem to be working out. All right, that's my review. Let's do some practice.